So alcohols can also be converted into alkenes via dehydration elimination reaction using phosphorus oxychloride and pyridine. Some organic compounds are susceptible to decomposition reaction in the presence of strong acids, and so some other methods need to be developed in order to convert alcohols into alkenes. And so one other common method that's used in the dehydration elimination reaction of alcohols is phosphorus oxychloride and pyridine. So here's an example. We have cyclohexanol undergoing dehydration elimination reaction using phosphorus oxychloride in the presence of pyridine. And this is what pyridine looks like. You can see that it looks just like benzene ring, except we're replacing a carbon and a hydrogen with a nitrogen with a lone pair. So what we get is an alkene, cyclohexene, with a double bond right here. This phosphorus oxychloride basically does the same thing as a strong acid in acid catalyzed dehydration. So they both convert the hydroxyl group into a much better leaving group. And then dehydration proceeds via E2 mechanism, as we shall see in the next slide. So here's the reaction mechanism. You can see that this phosphorus oxychloride is actually acting as a Lewis acid. You can see that this phosphorus atom right here is extremely electron deficient. You have a lot of electronegative atoms bonded to the phosphorus atom. And so in that case, this alcohol, the cyclohexanol here, is acting as a Lewis base, attacking this electron deficient phosphorus, which then results in the cleavage of this bond between the phosphorus atom and one of the chlorine atoms. And so what you have is a sigma bond between the oxygen and the phosphorus atom, as shown here. So this also creates a positive charge on the oxygen atom. So again, this is the first step. The second step is the deprotonation of the pyridine. So this is when pyridine comes into play. So the pyridine molecule will deprotonate this hydrogen, and the sigma bond breaks between the oxygen and the hydrogen atom, removing that positive charge on the oxygen atom. And so for the third step is basically the E2 mechanism. So another pyridine molecule will deprotonate a hydrogen on a beta carbon atom, which results in the cleavage of this bond between the alpha carbon and the oxygen atom, resulting in the formation of a double bond, a pi bond. So this is the product of this E2 reaction. So dehydration elimination reactions can be used in the synthesis of natural products, such as vitamin A and patchouli alcohol. So for vitamin A, for the synthesis of vitamin A, you can use strong acids, whereas for patchouli alcohol, you can use the dehydration elimination reaction involving phosphorus oxychloride and pyridine. Alcohols can also be converted to alkyl halides via substitution reactions. So we can use strong acids, we can use thionyl chloride in the presence of pyridine, as well as phosphorus tribromide. So again, there are multiple different ways to convert alcohols into alkyl halides. One of them is by using strong acids, such as hydrobromic acid and hydrochloric acid. So we can convert primary alcohols, secondary and tertiary alcohols into alkyl halides. The conversion of alcohols to alkyl halides basically happen via substitution reaction, and so you can see that the alcohol or the hydroxy group here is substituted with the bromine atom. Same thing over here with the reaction with hydrochloric acid. You can see that the hydroxy group is replaced by the chlorine atom. In terms of the rate of reaction of alcohols with acids, you can see that tertiary alcohols usually react much faster compared to secondary or primary alcohols. So more substituted alcohols usually react more rapidly with acids. So we say usually because primary alcohols react much faster via SN2 reaction compared to secondary or tertiary alcohols. So here's practice problem number 16. Draw the products of each reaction. So again, this is all alcohols here undergoing substitution reaction. We have a tertiary alcohol, a secondary alcohol, and another secondary alcohol here. So you can see that we don't really have a primary alcohol here. So remember that primary alcohols will only undergo SN2 reaction mechanism, whereas secondary and tertiary alcohols will undergo SN1 mechanism. And so with SN2 mechanism, there's always an inversion involved at the stereogenic center. And so since this is all going to be an SN1 mechanism, and you'll see a lot more examples later on, all we have to do is replace the hydroxy group with the halogen atom. And so that's what we're going to do here. So the first one here, we have a tertiary alcohol, and we're going to replace the hydroxy group with a chlorine atom. And this is the alkyl halide produced by this chemical reaction here. And for the second part here, again, we're just going to replace that hydroxy group with the halogen. And for the third one here, the same thing. Replace it with a bromine atom. So these are the products of these substitution reactions. So the reactivity of alcohols with acids and the reaction mechanism will depend on the structure of the alcohol itself. So for example, methyl and primary alcohols will undergo SN2 mechanism, whereas secondary and tertiary alcohols will undergo SN1 mechanism. In both cases, the first step is the protonation of this oxygen atom with the acid via proton transfer reaction. And so we're basically turning this hydroxy group into a better leaving group, followed by either SN1 or SN2 reaction. So here's the reaction mechanism of primary alcohols with acids via SN2. So the first step here is the proton transfer reaction with the primary alcohol and the acid, which results in formation of a better leaving group, in which the oxygen is protonated. And then the bromide ion is acting as a nucleophile, which attacks this primary carbon here, which results in the cleavage of the bond between the carbon and the leaving group. And this results in formation of the alkyl halide. Secondary and tertiary alcohols, on the other hand, react with acids via SN1 mechanism. So here we have a tertiary alcohol undergoing proton transfer reaction with hydrogen bromide, which results in the protonation of the oxygen, as shown here. The sigma bond between the oxygen and the carbon breaks, water leaves, resulting in the formation of a tertiary carbocation, followed by the nucleophilic attack of the bromide ion, resulting in the formation of the alkyl halide. You should also remember that the reactivity of hydrogen halides increases with increasing acidity. So you can see that hydrogen iodide is higher in acidity and also in reactivity compared to hydrogen bromide and hydrogen chloride. The chloride ion, however, is considered a poorer nucleophile compared to the bromide ion or the iodide ion. And so reaction involving primary alcohols with hydrogen chloride requires a catalyst, usually zinc chloride. And so zinc chloride here is acting as a Lewis acid, in which the oxygen atom attacks this electron-deficient zinc atom, resulting in the formation of a complex. And this complex right here is considered a good leaving group, which facilitates an SN2 reaction. So chloride ion will then attack this carbon atom, resulting in the cleavage of the bond between the carbon and the oxygen atom, resulting in the formation of the alkyl halide. Knowing the reaction mechanism is very important because it allows us to predict the stereochemistry of the products when the reaction happens at a stereogenic chiral center. So for example, primary alcohols react via SN2 mechanism, and so there's going to be an inversion of the structure at the stereogenic center. On the other hand, secondary and tertiary alcohols react via SN1, and so there's going to be racemization at the stereogenic chiral center because the nucleophile can attack on either side of the plane, a backside attack or a front side attack. Here's an example. Draw the products in stereochemistry for each reaction. For the first one here, you can see that we have a stereogenic center because we have 4 groups bonded to this carbon atom. However, this carbon atom is considered a primary carbon because it's only bonded to one other carbon atom. And so what we have here is a primary alcohol. So we can go ahead and write it down. We have a primary alcohol here. And so the very first step of this reaction would be protonation of this oxygen atom. And so we have 2 lone pairs here that will attack the hydrogen, and then the pair of electrons will migrate towards the bromine atom. And so what we have now is going to be a protonated oxygen with a positive charge. And so again, we have a deuterium here, and then this is a hydrogen, and then we have a methyl group. And so now, because we have a primary alcohol, the bromide ion is going to act as a nucleophile. So we have a bromide ion here, which will act as a nucleophile attacking this carbon via backside attack. So let me use a different color here. Alright, and the bond between the carbon and the oxygen will break, resulting in the formation of the alkyl halide. So we have a bromine atom here. Hydrogen in the methyl group, and then deuterium. Alright, and of course, water is the leaving group, a byproduct. And for the second question here, we also have a stereogenic center, again, because we have 1, 2, 3, 4 different groups bonded to this carbon. And so we have a chiral carbon reacting with the hydrogen chloride. And so you know that hydrogen chloride will require a catalyst, and so we're going to need a zinc chloride here as a Lewis acid catalyst. And so in that case, we're going to need a catalyst here, and that's zinc chloride. And so this oxygen atom here on the hydroxy group contains lone pairs of electrons, and so it's going to attack this electron deficient zinc atom. Let me use a different color here. So we'll attack this zinc atom, and so now we're going to have a positively charged oxygen, which makes this a better leaving group. Alright, so let me draw the structure here. So we have a phenyl ring or a benzene ring here. And so now we have a positively charged oxygen with a hydrogen bonded to a zinc chloride. And of course, that zinc will bear a partial negative charge. And we have the ethyl group bonded to that carbon hydrogen or chiral carbon. And so now we have a 1, 2, 3, a tertiary carbon here. So most likely this is going to undergo SN1 mechanism, and so this leaving group will leave. And so what we have is a tertiary carbocation. So we're going to have a tertiary carbocation right over here. And so there's a positive charge on this carbon. So we have a positive charge here. And then so now we have the chloride ion that will act as a nucleophile, which will then attack this carbocation either via front side or back side. And so we're going to have racemization here. We're going to have two different products. Okay, so the first product will have retention of its structure. So looks something like this. Chlorine atom, and then the ethyl group. Now let me create some space here. And then the other product will have an inverted structure, and so we can just draw that right down here. And so it's going to be an enantiomer here. So now we have the chlorine atom facing the front, and then the methyl group at the back. Alright, so those are the two products of this racemization reaction. So here's practice problem number 17. Draw the products of each reaction indicating the stereochemistry around any stereogenic centers. So for the first one here, you can see that we do have a stereogenic center because this carbon atom is bonded to 1, 2, 3, 4 different groups. So there is a hydrogen atom that's facing towards the front. So this is a primary carbon, which makes it a primary alcohol. And again, that carbon is a stereogenic center. And so this is reacting with hydrogen iodide. And so this is going to undergo SN2 reaction. Alright, so what we have here is going to be an inversion of the structure. And so it's basically going to replace the hydroxy group with the iodide ion. All right, and so this is the result. So as you can see, there's going to be an inversion of the structure because we have a chiral carbon here, a stereogenic center. And so instead of just retaining the structure, the iodine will now be facing towards the front. And for the second reaction here, you can see that this alcohol is a tertiary alcohol. And the carbon here is not considered a chiral center or chiral carbon because of the fact that these two carbon atoms are equivalent. They're the same. And so in that case, this is not a chiral center. And so again, because this is a tertiary carbon or tertiary alcohol, this is going to undergo SN1 reaction. And so we're going to have a racemization here. So the first product is this. So the first product will have the retained structure, and the second product will be this. So as you can see, when you compare the two structures here, these are actually similar. These two are similar structures. And so we have an identical structure here. So in that case, we only have one single product for this chemical reaction. And for the third reaction here, you can see that we have 1, 2, 3 a tertiary alcohol. And then you can see that this carbon here is considered a stereogenic center. And again, since we're reacting this with the hydrogen chloride, this is going to require a catalyst, zinc chloride. And so what we're going to have is a racemization here, okay, because we do have a chiral center, and the fact that we have a tertiary carbon or tertiary alcohol, this is going to undergo SN1 mechanism. And so the first one is going to have a retained structure. And the other product will have an inverted structure. So it's going to look something like this. So we're basically switching the chlorine and the methyl group here. And so this is going to be the chlorine atom right here. And then now we have a methyl group facing towards the front. All right, so these two are the two products of the SN1 reaction shown here. So earlier I mentioned that rearrangement is possible for any reaction mechanisms involving the formation of a carbocation. And so since both the SN1 and E1 reaction mechanisms involve the formation of a carbocation, rearrangements via a hydride shift and a methyl shift are therefore possible. So here's an example. Draw a stepwise mechanism for the following reaction. So you can see that we have a secondary alcohol here. So this is a secondary alcohol reacting with the hydrogen bromide or hydrobromic acid to form the tertiary alkyl halide. All right, so the very first step of this SN1 reaction is protonation of this oxygen. So there's going to be a proton transfer reaction happening between the alcohol and the acid. So let's take a look. So this alcohol is basically acting as a base, attacking this hydrogen here, which results in the protonation of the oxygen atom. So we're basically turning this hydroxy group as a better leaving group. So what we have is a protonated oxygen. All right, so the next step here is the cleavage of this bond between the carbon and the oxygen atom. which results in the formation of the carbocation. All right, so here's our secondary carbocation here. So I'm just going to label this secondary carbocation. All right, and notice that there's actually a hydrogen bonded to this carbon atom here. So there's a hydrogen here, and so therefore there's going to be a 1,2 hydride shift. So this hydrogen will migrate towards this carbon bearing the positive charge. And so what we have is the formation of a tertiary carbocation. So now this carbon right here has a positive charge. And then the bromide ion that was generated during the first step will act as a nucleophile attacking this electron deficient carbon atom. And so this results in the formation of the tertiary alkyl halide. So now let's take a look at two other ways in converting alcohols to alkyl halides. So we just looked at how alcohols can be converted to alkyl halides using acids. So now we're going to take a look at how thionyl chloride mixed with pyridine and also phosphorus tribromide can be used to convert alcohols into alkyl halides. So both primary and secondary alcohols can be converted into alkyl halides using thionyl chloride and phosphorus tribromide. If we use thionyl chloride, we can convert alcohols into alkyl chlorides, whereas phosphorus tribromide results in the formation of alkyl bromides. In both cases, the reaction will undergo SN2 mechanism, as we shall see in the next few slides. So first, let's take a look at the conversion of a primary or secondary alcohol using thionyl chloride in the presence of pyridine. And so here you can see that we have two different alcohols here. We have a primary alcohol and a secondary alcohol. If you treat them with thionyl chloride in the presence of pyridine, what we get are a primary alkyl chloride and secondary alkyl chloride respectively. And then we get two different types of byproducts here. We get sulfur dioxide and hydrogen chloride or hydrochloric acid. The mechanism of this reaction consists of two parts. The first part is converting this bad leaving group, hydroxy group, into a much better leaving group, followed by the nucleophilic substitution via an SN2 reaction. And since this is a substitution reaction, we're basically substituting or replacing this hydroxy group with a chlorine atom. And so what we get is a primary alkyl halide or alkyl chloride. Same thing over here, we're replacing the hydroxy group with a chlorine atom, which results in the formation of the secondary alkyl chloride. So here's the reaction mechanism for the conversion of a primary alcohol or a secondary alcohol into an alkyl chloride using thionyl chloride in the presence of pyridine. And again, this will undergo SN2 mechanism. So here we have, again, a primary alcohol or a secondary alcohol attacking this electron deficient sulfur atom, which results in the formation of a sigma bond between the oxygen and the sulfur atom, and the cleavage of a sigma bond between the sulfur and the chlorine atom, as shown here. And then the next step is deprotonation. So this oxygen will be deprotonated. So this hydrogen is removed by the pyridine, as shown here. So now the third step is the SN2 mechanism. So we have a chloride ion, which acts as a nucleophile, which will then attack this electron deficient carbon atom on the R group, resulting in the cleavage of the sigma bond between the carbon atom on the R group and the oxygen atom. So this part right here is the leaving group. And then the sigma bond between the sulfur and the chlorine atom will also break, which results in the formation of sulfur dioxide and a chloride ion. And so now we have this organic product, the alkyl chloride. Here's practice problem number 19. If the reaction of an alcohol with thionyl chloride and pyridine follows an SN2 mechanism, what is the stereochemistry of the alkyl chloride formed from R-butan2-ol? So the first thing that we should do here is to draw the structure of R-butan2-ol. So butanol has a total of 4 carbon atoms. And then on the second carbon atom, there's a hydroxy group. So if this is my first carbon atom here, this is my second carbon atom, then we have a hydroxy group bonded to that carbon. And so now we have to specify the configuration because of the stereochemistry here. We have an R configuration. And so if the hydroxy group has the highest priority, then this is labeled 1. And then this second carbon right here, or this third carbon, is going to be the second highest priority. And then the first carbon will be the third highest priority. And then, of course, there's a hydrogen that's bonded to this carbon atom here. And so when we connect the numbers here, you can see that it goes in the clockwise direction. And so we know that this is an R group. And the highest priority should be oriented facing towards the front. And so in that case, we can just change this, specify the orientation. So it's oriented towards the front of the plane. And then, of course, we have a hydrogen that's sticking out at the back, all right, which has the lowest priority here. So if we were to react this with thionyl chloride, SOCl2, in the presence of pyridine, there's going to be an inversion of the structure at the chiral center, at the stereogenic center. So if you remember that this is a stereogenic center because it contains 4 different groups here. And so now what we get is an alkyl chloride. So you're basically just replacing this hydroxy group with a chlorine atom. But because there's an inversion, that chlorine atom is going to be facing towards the back. All right, so let's draw the product here. We have 4 carbon atoms. And then now we have the chlorine atom facing towards the back. So this is the inverted product here. So in that case, the configuration of this alkyl chloride, let's see. So we have 1, 2, and 3. And because this is oriented towards the back, it's going to be an S configuration. All right, and that's it. So this is the product of this SN2 reaction. So primary and secondary alcohols can also be converted into an alkyl bromide using phosphorus tribromide. So here you can see that we have a primary alcohol and a secondary alcohol, which can then be converted into primary alkyl bromide and secondary alkyl bromide respectively. And we have a single byproduct as shown here. The mechanism of this reaction consists of 2 parts, similar to when we use thionyl chloride in the presence of pyridine. The first part is the conversion of the bad leaving group into a better leaving group, followed by nucleophilic substitution by bromide ion via an SN2 mechanism. So here's the reaction mechanism when using phosphorus tribromide in converting alcohols into an alkyl bromide. So here we have an alcohol. Again, this can be a primary alcohol or a secondary alcohol, which would then react with the phosphorus tribromide by attacking this electron-deficient phosphorus atom. And so we have a sigma bond that will be formed between the oxygen atom and the phosphorus atom. And this also results in the cleavage of the sigma bond between the phosphorus and the bromine atom, as shown here. And then the second step is the SN2 reaction, in which the bromide ion that was generated in the first step is acting as a nucleophile, which would then attack the carbon atom on this R group, which results in the cleavage of the bond between the carbon atom on this R group and the oxygen atom. So this is the leaving group right here, which then results in the formation of the alkyl bromide and the byproduct. So here's practice problem number 20. If the reaction of an alcohol with phosphorus tribromide follows an SN2 mechanism, what is the stereochemistry of the alkyl bromide formed from R-butan-2-ol? So this is similar to the reaction that we looked at earlier using thionyl chloride in the presence of pyridine. And so let's go ahead and first draw the structure of this alcohol here. So here's the structure of the alcohol. So we have the hydroxy group oriented towards the front of the plane. And so this chiral carbon right here has an R configuration. All right, and so if we were to react this with phosphorus tribromide, we're basically replacing this hydroxy group with a bromine atom, except it's going to be facing towards the back. Because again, this is an SN2 reaction, and so there's going to be an inversion of the structure at the stereogenic center. All right, so this is going to be an S configuration. For number 21, draw the organic products formed in each reaction and indicate the stereochemistry of products that contain stereogenic centers. So for the first alcohol here, you can see that this is a primary alcohol and that there's no stereogenic center here because this carbon is bonded to two hydrogen atoms, so two of the groups are similar. And so what we have is basically a replacement. So we're basically substituting this hydroxy group with a chlorine atom. So we have 1, 2, 3, 4, 5 carbon atoms. 1, 2, 3, 4, 5. And then we're replacing this hydroxy group with a chlorine atom. So this is going to be the product of this substitution reaction. For the second reaction here, you can see that we have a tertiary alcohol. So we have a tertiary alcohol. So that means that this is going to undergo SN1 mechanism rather than SN2 because a tertiary carbocation is pretty stable compared to a primary or secondary alcohol carbocation. And so in that case, this hydroxy group is going to be protonated, followed by a nucleophilic attack coming from the iodide ion. And so what we have is going to be a racemization. There's going to be racemization because of the fact that there's a chiral center right over here, a stereogenic center. And so in that case, we're going to have a mixture of products. We have one is going to be, or one is going to have a retention of the structure, and the other one is going to be an inversion. All right, so these are the two products of this chemical reaction. And for the last one here, we have a secondary alcohol. And you can see that this carbon right here is a chiral carbon or stereogenic carbon. And so there's going to be an inversion of the structure here at the chiral center. And so we're basically just replacing this hydroxy group with a bromine atom. But the only difference is the bromine atom is going to be oriented towards the back of the plane. And so in that case, we have a cyclopentane ring, a methyl group here, and then a bromine atom. And that's it. So here's a table that basically summarizes what we talked about regarding converting alcohols into alkyl halides. So you can see that we have different types of alcohols here, the different classifications of alcohols. We have methanol, primary, secondary, all the way to tertiary alcohols. And these are here's a list of the different reagents that you can use in converting these alcohols into alkyl halides. So for example, here you can use any of these reagents in converting methanol into an alkyl halide, and it will undergo via SN2 reaction only. You can also use the same reagents here for primary alcohols, and they will also undergo via SN2. However, for secondary alcohols, the first two here, phosphorus tribromide and thionyl chloride in the presence of pyridine, will only undergo SN2 mechanism. But you can react secondary alcohols using acids in order to convert them into an alkyl halide, but via SN1 reaction. And finally, tertiary alcohols can also be converted into alkyl halides via SN1 reaction using strong acids. And here's another table that basically contains the same information that I showed you in the previous slide. Another organic reaction involving alcohols is called tosylation, and we're basically converting alcohols into alkyl tosylates. In this process, we're turning that hydroxy group into a better leaving group called the tosylate group. So an alkyl tosylate is composed of two parts. The first part is the alkyl group derived from an alcohol. And then the second part is called the tosylate group, short for p-toluenesulfonate, which is considered a good leaving group. So in the process of tosylation, we're basically replacing this hydrogen atom with the tosyl group. So this is what a tosyl group looks like, and it has the symbol TS. And so notice that this sigma bond right here is not broken. So the sigma bond between the carbon atom and the oxygen is not broken. And so you can't really consider this a substitution reaction. And that's why tosylation is a completely different organic reaction. And so alkyl tosylates are given the symbol R-OTS or R-OTS because it contains a tosyl group that's bonded to an alkyl group derived from an alcohol. So we can convert alcohols into alkyl tosylates using p-toluenesulfonyl chloride, abbreviated TSCl, in the presence of pyridine. So we're essentially converting that poor leaving group, hydroxy group, into a good leaving group, the tosylate group. And this process works for primary, secondary, and tertiary alcohols. So here's an example. We have a primary alcohol undergoing tosylation, and so we're basically reacting this alcohol with TSCl, or p-toluenesulfonyl chloride, in the presence of pyridine. And so what happens is that this hydrogen is replaced by the tosyl group, as shown here. So we can just rewrite this and abbreviate this into an alkyl group, followed by OTS. So here's an example showing you the reaction mechanism in the tosylation process. We have an S-butan-2-ol reacting with p-toluenesulfonyl chloride in the presence of pyridine. In this process, the alcohol is acting as a nucleophile, attacking this electron-deficient sulfur atom, which results in the cleavage of the sigma bond between the sulfur and the chlorine atom, creating a positive charge on the oxygen atom, as shown here. And this step is followed by deprotonation by pyridine, which results in the formation of the alkyl tosylate. You might want to take note that the configuration is retained here because of the fact that the sigma bond between the carbon and the oxygen was never broken. Here's practice problem number 23. Draw the products of each reaction and indicate the stereochemistry at any stereogenic center. So in this first example here, you can see that we have a primary alcohol. So this is a primary alcohol. So that means that this carbon right here is not a stereogenic center because it contains two hydrogen atoms bonded to it. And so what we can do is we can just replace this hydrogen atom with the tosyl group. And that's it. So this is the product of this chemical reaction. And for the second example here, you can see that we have a secondary alcohol. So this is a secondary alcohol. And basically, we're replacing this hydrogen atom again with the tosyl group. And so we have 1, 2, 3, 4, and then oxygen, and then TS. So again, in the tosylation process, the configuration is retained because this carbon to oxygen bond is never cleaved or broken. So once you've converted an alcohol into an alkyl tosylate, you can perform a lot of organic chemical reactions such as substitution reaction and elimination reaction. And alkyl tosylates are usually treated with strong nucleophiles, which would favor substitution reaction via SN2, or strong bases, which would then favor elimination reaction via E2 mechanism. So here are two examples. We have propyl tosylate, which can react with a strong nucleophile, which would undergo an SN2 reaction, resulting in the formation of a substitution product. You can also react an alkyl tosylate with a strong non-nucleophilic base, such as the tert butoxide here, which would undergo proton transfer reaction, resulting in the formation of an alkene, which is an elimination product. So for substitution reactions via SN2 mechanism, you should always keep in mind and take into account inversion of configuration at the stereogenic center. And so over here, if we have a stereogenic carbon, then you know that there's going to be an inversion of configuration. Let's say from R to S or from S to R. Here's an example. Draw the product of the following reaction, including stereochemistry. So here we have a primary carbon that's bonded to the oxygen atom. And so you know that this is going to undergo SN2 mechanism because we also have a strong nucleophile right here. So this is an alkoxide ion. So let's write that down. So we have a primary carbon right here and a strong nucleophile. So this is a nucleophile. We have an alkoxide. So that's a strong nucleophile here. Alright, so what happens is this oxygen will attack this electron deficient carbon via backside attack. And so we're going to have a inversion here because we have a deuterium and there's also a hydrogen atom here. And so what we get is an inverted product. So we have 1, 2, 3, 4 deuterium, inversion of configuration, and then OCH2, CH3. Here's practice problem number 24. Draw the products of each reaction and include the stereochemistry at any stereogenic center in the products. So for the first example here, you can see that we have a primary carbon that's bonded directly to the oxygen. So this is a primary carbon. And then we have a good nucleophile, but this is considered a weak base. And so this is going to undergo SN2 mechanism. Okay, so this is going to undergo SN2. And so it's going to be a substitution reaction, and there's not going to be an inversion here because this carbon right here is not a stereogenic center. And so we're essentially substituting this OTS for CN, and so the product is going to look something like this. We have 1, 2, 3, 4, and then the cyanide. And that's it. So this is the product of this substitution reaction. And for the second reaction here, you can see that we have a primary carbon connected to this oxygen atom. So this is a primary carbon atom. And then we have a strong non-nucleophilic base. So this is tert butoxide right here. So this is a strong non-nucleophilic base. And so that means that we're going to have an elimination reaction here. And so the base will deprotonate a hydrogen on a beta carbon. And so if this is the alpha carbon right here, then this is the beta carbon. And so this beta carbon contains 2 hydrogen atoms. And so the base will deprotonate one of these hydrogens. And so what we have is, I'm going to move this right over here. It's going to be a double bond that will form between the alpha carbon atom and the beta carbon. Alright, so that's basically it. So the tosylate here is the leaving group. And so we have a double bond between the alpha and the beta carbon as shown here. So even though we only really care about the organic products here, we should probably include the byproducts as well. So we have, for the first reaction, OTS with a negative charge. And then for the second reaction here, we have K plus and the OTS with a negative charge plus the tert butanol here. So that's HO. CH3. And for the third one here, you can see that we have a secondary carbon right here, and this carbon is also considered a stereogenic center. And so we have a secondary stereogenic carbon here, and so there's going to be an inversion of the structure because we have a strong nucleophile right here. So this bisulfide ion is considered a strong nucleophile, and so this is going to undergo SN2 mechanism. So that's a strong nucleophile, and so in that case we're going to have an inversion at the stereogenic center. So there it is. So this is the product of this chemical reaction, and we should include the byproducts as well. So we're going to have an OTS with a negative charge. And for the last reaction here, you can see that we have a tertiary carbon atom. So this right here is a tertiary carbon atom. And over here we have a salt. We have a sodium ethoxide, and this ethoxide ion is considered a strong nucleophilic base. So that means it's both a strong base and a strong nucleophile. And so we have a strong nucleophile, but it's also a strong base. Okay, so this is also a strong base. And so since we have a tertiary carbon, most likely this reaction will undergo E2 elimination reaction. And again, the reason why is because we have a tertiary carbon right here. And so it would favor elimination reaction over substitution reaction. All right. And so in that case, we're going to have to identify the beta carbon atoms here. So if this is the alpha carbon, then we have a beta carbon here, here, and over here. And so a double bond will form between the beta carbon atoms and the alpha carbon. And so we're going to have several different types of products here. So the first one is going to be a double bond between this alpha carbon and this beta carbon right here. And then of course the single bond between the tosylate and this carbon atom will break, forming that double bond between the alpha carbon and the beta carbon. Alright, so this is one product. And then the other one will have a double bond between the alpha and this beta carbon atom right here. And finally the third, so let me just create some space here. And the third product is going to have a double bond between this alpha carbon and this beta carbon atom right here. So double bond here. All right. And as you can see, these two, the first two products right here are going to be the major products because they are tri-substituted. Whereas over here we have a di-substituted double bond. And so these are going to be the major products right here. And this one is going to be the minor product. So every time you encounter a chemical reaction involving tosylation followed by an SN2 mechanism, you have to always remember that there's going to be an overall inversion of the structure at the stereogenic center. And so here, for example, we have a cis 3-methylcyclohexanol undergoing tosylation, which results in the retention of the structure at the stereogenic center, followed by an SN2 reaction, which then results in the inversion because this is a leaving group right here. This tosylate ion is going to be a leaving group, which results in the inversion of the structure at the stereogenic center. So now we have a trans molecule here. So from cis to trans. So here's the summary of nucleophilic substitution and beta elimination reactions of alcohols. So you can basically turn an alcohol and convert it into an alkene by using any of these reagents here. And so if we use sulfuric acid, this can either go via E1 or E2 elimination reactions. So that would depend on the type of alcohol that you use. So if you use primary alcohols, then it will undergo via E2 elimination reaction, whereas for secondary and tertiary alcohols, they will undergo via E1 elimination reactions. You could also use phosphorus oxychloride in the presence of pyridine, and when using this combination, you can basically convert any type of alcohols into an alkene. So you can use primary alcohols, secondary or tertiary alcohols, and react them with phosphorus oxychloride in the presence of pyridine, and you'll get an alkene. So you can also convert alcohols into alkenes, which are elimination products or substitution products. But first, you would have to convert alcohols into alkyl halides. And you can do that by using either strong acids, thionyl chloride in the presence of pyridine, or phosphorus tribromide. And another method that you can use to convert alcohols into elimination products or nucleophilic substitution products is by first converting this hydroxy group into a better leaving group via what they call tosylation. And so you can use p-toluenesulfonyl chloride in the presence of pyridine to convert this hydroxy group into the tosylate group, followed by either elimination reaction or nucleophilic substitution reaction. So here's practice problem number 26. Draw the product formed when isopropyl alcohol is treated with each reagent. So the first one here is thionyl chloride in the presence of pyridine. And so let's draw the structure of isopropyl alcohol. So this is what isopropyl alcohol looks like. And you can see that this is a secondary alcohol. So any primary and secondary alcohol reacting with thionyl chloride in the presence of pyridine will undergo SN2 mechanism. And so let's draw thionyl chloride here. So this is thionyl chloride. And the secondary alcohol, isopropyl alcohol, will attack this electron-deficient sulfur, resulting in the cleavage of the bond between sulfur and chlorine. Alright, so a sigma bond will be formed between oxygen and sulfur, creating a positive charge on this oxygen atom. Alright, and then we have the pyridine, which contains a lone pair of electrons, will deprotonate this hydrogen right here via proton transfer reaction. And then the sigma bond between the hydrogen and oxygen will break. And then you have the transfer of electrons towards the oxygen atom. And so what we have is shown here. And then the chlorine atom, or the chloride ion here, will act as a nucleophile, which would then attack this electron-deficient carbon atom right here. So this is the SN2 reaction. So the sigma bond between the carbon atom and the oxygen atom will break. And then the sigma bond between the chlorine atom and the carbon will form, resulting in the formation of the product. And for the second reaction here, we have isopropyl alcohol reacting with p-toluenesulfonyl chloride in the presence of pyridine. So this is going to undergo tosylation here. So let's take a look. So we have isopropyl alcohol, and this will react with TSCl. So this is what TSCl looks like. Alright, so basically we have this alcohol acting as a nucleophile. So it will attack this electron-deficient sulfur. And then the sigma bond between the sulfur and chlorine atom will be cleaved. And then the sigma bond between the oxygen and sulfur atom will form, creating a positive charge on this oxygen atom. All right, and then we also have pyridine here, which will undergo proton transfer reaction, deprotonating this hydrogen right here. So we have pyridine with a lone pair, which will then undergo proton transfer reaction, cleaving the bond between hydrogen and oxygen atom. So what we have is the formation of R-OTS. So this is the product of the tosylation process. And for the third one here, we have sulfuric acid reacting with the alcohol. So we have a secondary alcohol here. And so any secondary or tertiary alcohol reacting with sulfuric acid will undergo elimination reaction via E1 mechanism. So that means that we're going to have a carbocation that's going to be generated as a reactive intermediate. And so we have the alcohol here reacting with the acid. And so that means that the alcohol is going to act as a base. So we're going to have a proton transfer reaction here. And so the sigma bond between the hydrogen and oxygen will break. And then a sigma bond between the oxygen and hydrogen will form, creating a positive charge on this oxygen atom. All right, and so now we've turned this hydroxy group into a better leaving group. And so the next step here is the generation of the carbocation. So this part will break, which results in the formation of a carbocation. All right, and then the next step here is the reaction between the conjugate base that was generated on the first step and this carbocation here. So we're going to have the conjugate base, which would deprotonate one of the hydrogens here on the beta carbon. So if this is the alpha carbon right here with the positive charges, we have two beta carbons, which are actually identical. And so the hydrogen sulfate can deprotonate either beta carbon. And so let's just say that we have a hydrogen bonded right here. And let me create some space here. So this hydrogen sulfate will deprotonate this hydrogen, and then the sigma bond between the hydrogen and this beta carbon will break, forming a double bond between this beta carbon atom and this alpha carbon. So what we have is an alkene. Alcohols reacting with hydrogen bromide results in the formation of an alkyl halide, and so that means we're going to have a substitution reaction here. So we have isopropyl alcohol, which is a secondary alcohol, reacting with hydrogen bromide or hydrobromic acid. And so any secondary or tertiary alcohol reacting with a hydrogen halide will undergo substitution reaction via SN1 mechanism. And so that means that we're going to have protonation as the first step, and then carbocation will be generated. So this oxygen, this alcohol will react with this hydrogen bromide via proton transfer reaction, resulting in the formation of a positively charged oxygen. So we're basically turning this hydroxy group again into a better leaving group. And then the next step here is the generation of the carbocation. So the sigma bond between the carbon and the oxygen atom will break. And then finally, the nucleophilic attack by this bromide ion. And this results in the formation of the alkyl bromide. And for part E here, we have phosphorus tribromide, followed by the reaction with a cyanide ion. And so phosphorus tribromide is best for methanol, primary alcohols, and secondary alcohols. So PBr3 will undergo substitution reaction via SN2 mechanism. So let's take a look. Again, we have the isopropyl alcohol here, secondary alcohol, reacting with phosphorus tribromide. So the first step here is basically the formation of the sigma bond between oxygen and phosphorus atom, which creates a positive charge on the oxygen. And at the same time, the sigma bond between the phosphorus and the bromine atom will break. So what we get is this. Again, a positively charged oxygen. All right. And since this is undergoing SN2 mechanism, we're going to have a backside attack by a nucleophile. And the nucleophile is going to be the bromide ion that was generated from the first step. So there's the nucleophilic attack. This one leaves. And so what we have is an alkyl bromide. All right, and then the second part of the reaction is between the alkyl bromide and the cyanide ion. And so we have a cyanide ion that will undergo nucleophilic substitution. And what we have is the final product. And the last reaction here is between the alcohol and phosphorus oxychloride in the presence of pyridine. So let's take a look. So again, we have this alcohol here. So the very first step is the attack of the alcohol, forming a bond, a sigma bond between the oxygen and the phosphorus atom, cleaving this sigma bond between the phosphorus and one of the chlorine atoms, and generates this product right here. So the oxygen will bear a positive charge. All right, and then the next step here is deprotonation of this hydrogen atom by the pyridine. So we have pyridine here, which would then deprotonate this hydrogen. Sigma bond breaks. And so now we have this product here. All right, and then the next step here is elimination reaction. So we're going to have another molecule of pyridine, which would then deprotonate one of these beta carbon atoms. So these beta carbon atoms are identical, and so it doesn't matter whether it deprotonates this one or one of the hydrogens here. So let's just pick this hydrogen right here. So it will deprotonate this hydrogen, forming a double bond here, and this sigma bond breaks, and what we have is an alkene product. And there it is.